How do acids and bases work? You've read the textbooks, but how do they really work? Why is it so important to understand the concept of conjugate acids and conjugate bases? Keep watching to find out. Now, the topic of acids and bases and alkalis is so big, I've separated it into a series of videos that examine each aspect in detail. In this first video, we're going to look at how they actually work. But first, where did this concept of acids and bases start? Well, it goes all the way back to ancient times, at least 4,000 years ago. Our first record is from the Greeks, who invented a word, oxine, for things that tasted sour. That's where the word oxygen comes from. And now we know that sour is the taste of acid. Later, the Romans found a way to make super corrosive compounds from ash, and about 800 years after that, Arabic scholars developed these ideas into the concept of alkalis. These classifications turned out to be crucial during the development of chemistry until the surprisingly late period of the 1920s, when we finally settled on our modern definitions. The whole story of the emergence of acids and alkalis as an essential concept for chemistry is fascinating, and I'm working on a full video, so be sure to watch out for it. Okay, so the next point to cover is that there are two ways to talk about acids and bases: the Brønsted-Lowry definition and the Lewis definition. The Brønsted-Lowry definition is the version taught in high school, but the Lewis definition is way more comprehensive. And sure enough, a comparison of those two definitions is going to be the subject of a future video. So for this one, we're going to focus on the Brønsted-Lowry definition, which is, well, there's the original definition and there's the textbook definition. And for the moment, we'll keep things simple by quoting the typical textbook definition. An acid donates a hydrogen ion in a reaction, and a base receives a hydrogen ion. And in this case, hydrogen ion means a hydrogen atom that has lost its electron, leaving only the nucleus, which is just a proton with its positive charge. So there you go. Doesn't sound like much, does it? And hydrogen ions are tiny. But we'll see in another video that this tiny little ion changes everything. And by the way, I'm not saying hydrogen ion anymore, because hydrogen ion is a mouthful, and it's much easier to just say proton. And while we're about it, saying acids and bases every time is a mouthful too, so I'm just going to say acids for now, and we'll remember that the same things apply to bases, but the opposite way round. So let's start by looking at the first consequence of the Brønsted-Lowry theory, using the reaction between acetic acid and ammonia, which is a base. Every acid-base reaction involves one species losing a proton and another species receiving that proton. Whatever chemical is losing the proton is an acid in this reaction, and whatever chemical is getting the proton is a base in this reaction. Keep that in mind, because we're coming back to it in a minute. The vast majority of acid-base reactions are reversible, and that leads to the bit that sends everybody running and screaming. Are you ready? Let's go. Acetic acid gives away a proton to become acetate. And because the reaction can go backwards, the acetate can take a proton back, which means going this way, acetate is a base. So, because acetic acid and acetate come from the same molecule, we say that acetate is the conjugate base of acetic acid, because conjugate means partner. And of course, you could go the other way and say that acetic acid is the conjugate acid of acetate. Technically, you're not wrong, but the acid form is by far the most common one. And ammonia gets a proton to become ammonium. And likewise, the ammonium can give a proton back, which means ammonium is an acid. And technically, ammonia is the conjugate base of ammonium, but the base form is the most common. Now, if you don't get that, click back and watch it again until you do, because it comes up again and again in all kinds of chemistry, from self-healing concrete to batteries to organic chemistry to almost all biological chemistry. If you can see it in your mind's eye and see the connection between an acid and its conjugate base, everything will be so much simpler. Okay, so now we can understand the difference between strong and weak acids. A strong acid dissociates essentially completely in solution to give only protons and the conjugate base. And as far as I can see, the reaction is thermodynamically reversible, but the back reaction is so infrequent we usually forget about it. And so it should make sense that the conjugate base of a strong acid is a very weak base, but I prefer to call it a useless base, because technically it is a base, but it can't or won't take a proton from pretty much anything. The chloride ion, for example, is the conjugate base of hydrochloric acid, and yes, it does do some acid-base chemistry, but hardly anyone would call it a base, at least in the Brønsted-Lowry definition. And perhaps surprisingly, what makes a weak acid weak is the strength of its conjugate base. If the conjugate base is relatively strong, it will hold on to the proton harder, and we will get a greater proportion of the undissociated acid left in solution. So for a weak acid, the acid and its conjugate base are giving up and taking back protons all the time. And to understand how that works means understanding how chemical equilibria work. This is super important for acid-base chemistry, and I've made a playlist all about it, so be sure to check it out if you haven't already. And remember, everything works the same way for bases, but going in the opposite direction. The weaker a base is, the stronger its conjugate acid will be, because it's easier for the acid to release a proton back into solution. Now, don't forget how this works, because it's crucial to understanding mixtures called buffers, which are essential for controlling the acidity of things like food, our blood, fields of crops, and of course chemical reactions in the lab. And yes, there's a video coming up. Okay. So now we've covered the idea of strong acids and weak acids, we can also understand why the concept of concentrated and dilute acids is so important. Here I'm standing in the sea, which is full of billions and billions of molecules of hydrochloric acid, a strong acid. But amazingly, my legs are not dissolving. I am, however, freezing cold. I'm just interrupting to tell you how cold it was on that day. You can maybe tell because I've got that big puffy jacket on, but it was so windy. Those waves were massive. They were higher than me, and the beach just drops off as soon as you walk even just a couple of meters into the sea. So I was really scared, and I was just hanging around for about 15 minutes before I actually dared to go in the water. When I came out, my feet were numb, which was actually quite useful in the end because I had to walk down a stony path in bare feet and I couldn't feel a thing. But if you appreciate the lengths I go to make these videos, a quick click of the like button would cheer me up no end. Thank you. So where were we? Yes, hydrochloric acid in the sea, not dissolving my legs. And now we go on to pure acetic acid. It's basically concentrated vinegar, but I wouldn't dare put this on my chips. So what's going on? Well, what happens in a reaction mixture isn't determined so much by which kind of acid we're using, so much as what the acidity of the mixture is. And what that means is how many protons are freely available to cause trouble. Very simply, we need a small concentration of a strong acid or a much larger concentration of a weak acid to release the same number of protons. So the strong hydrochloric acid in the sea is very dilute, which is why my legs don't dissolve, while the weak acetic acid in this beaker is very concentrated, which is why this chip dissolves. This bottle has a warning symbol on the label, and I wear gloves just to pick it up. Smells great though. And as always, everything is just the opposite way round for bases. You only need a small concentration of a small base to get the same basicity as a concentrated solution of a weak base. Which brings us onto the concept of pH. I'm sure you already know that textbooks say pHs under 7 are acidic, over 7 are basic, and 7 is neutral. But it's actually way more interesting than that, which is why that's going to be a dedicated video too. But let's go back to our simple explanation of how acids and bases work. At the beginning of the video, I told you that there was something fishy about the textbook description, didn't I? After all, why does an acid donate a proton? Well, they don't. Not really. So, how do acids really work? Before we answer that, I'd just like to say this video is produced at Kyushu University. It's one of Japan's top universities, and we've got courses in science and engineering in English. A great alternative in these uncertain times. So check out the link in the description. So, if acids don't really donate protons, what do they do? Some chemists say that it's better to focus on the bases, that acid-base chemistry is really about bases taking protons, and acids are just very poor at holding on to them. And that's okay, but I think even that approach is a big simplification. A more accurate explanation is that protons are leaving and joining molecules all the time, even from parts of a molecule that we don't usually think of as being acidic. But acidic molecules have at least one hydrogen that is relatively easy to move, and that word relative is important here, because whether we consider a hydrogen to be acidic or not depends on the situation, just like other words such as tall, short, heavy, or light. For example, most of the time we don't consider an alcohol hydrogen to be acidic, but they can't resist very strong bases such as Grignard reagents. Grignards are such strong bases we have to make sure we haven't got any alcohols in the pot if we're using them, because they'll just get neutralized before they do the job we made them for. And Grignards are a pain in the neck to make, so you don't want to waste them. So, what do we mean when we call a molecule an acid? We mean somewhere it has a proton that comes off relatively easily and stays off for a relatively long time, at least long enough to get the job done. And in organic chemistry especially, most protons will not be acidic, which is why it's significant when one is. But it's all very well saying that a proton comes off easily, but why is it so easy? Well, there are two things. Let's start by looking at the proton itself. If it's sunk deep in a cloud of electrons, it will be difficult to get it out. That's why it's very difficult to remove protons from alkanes, for example. But if the proton is bonded to a very electronegative element, such as oxygen or chlorine, then those elements will pull all the electron density to themselves, leaving the proton with a high, partially positive charge density, which means it's unstable and vulnerable to being picked off by an atom that's offering a bigger electron cloud, such as nitrogen. But how easily the proton comes off is only half of the story, because the other thing we have to consider is, what is the proton leaving behind? In other words, what is the conjugate base? I told you they were important. The stability of the conjugate base determines how long the proton can stay away once it's left. If the conjugate base is very stable, it won't take the proton back again, or take one from another molecule. This explains why alcohols are very weak acids, but carboxylic acids are just weak. The conjugate base of an alcohol is called an alkoxide. The oxygen atom got greedy, pulled the electron density away from the proton, and it got picked off by a strong base. But oxygen is a small atom, and a full negative charge is too much charge density for it to remain stable. So the alkoxide will either take the proton straight back, or just take one from a neighbouring molecule, which is why you can't have a stable solution of alkoxides in water, for example. But let's take a look at this carboxylic acid. This part here looks just like an alcohol, but there are two differences compared with real alcohols. Firstly, this carbon atom is doubly bonded to another oxygen atom, which pulls away even more electron density from the poor proton. But on top of that, and perhaps more importantly, the conjugate base is stabilized by something called resonance. I won't go into the details here, but resonance means the negative charge can be spread over these three atoms, which reduces the charge density, and that means it's stable enough to not need a proton for a significant amount of time. And that's why acetic acid is an acid. But now we know this, we can see that in a real reaction mixture, there are all kinds of places where a proton might find itself. Perhaps deep within the electron cloud of an alkane, exposed on the outside of a carboxylic acid that doesn't particularly care if it comes back, or part of a water molecule that can't even decide if it's an acid or a base. What that means is that protons shuffle all around the reaction mixture, spending most of their time in stable electron clouds or attached to unstable conjugate bases that won't let them leave. So, anytime we take a snapshot of where they all are, we find them collecting in the most stable little niches where they have plenty of electron density to neutralize their positive charges. The places they've left are the acids, and the places they've gone to are the bases. But that's a lot to imagine, and a lot to describe in words. And you know what's much easier, much simpler, and is just as useful? Simply saying that acids donate protons and bases accept them. Now, you might have noticed that I haven't talked much about bases in this video, and that's because it's better to use Lewis acid-base theory for bases. As I mentioned before, there's another video coming up, so be sure to subscribe if you don't want to miss it. And there are so many other things to say about acids and bases, so tell me in the comments what you want to see in this series. And a big thank you to my supporters on YouTube memberships and Patreon who enable me to make these videos, especially the animations. Now, if you want to see an awesome animation of acids attacking a protein, click this video here. I've been waiting years to make it. And if you've already seen it, here's one YouTube chose for you, and I'll see you again in the next one. Bye-bye.